Hello again, everyone. My name is Tony Record. I'm an AP Calculus teacher at Avon High School in Avon, Indiana, and I am here to deliver a video that will help both teachers and students understand some of the scoring intricacies from the 2022 AP Calc AB exam, question AB6. Now, of course, this was the last free response question on that particular exam, and its focus was on particle motion. In this particular problem, we had two particles moving, one along the x-axis and one along the y-axis. So let's go ahead and take a look at the stem of the question here. It reads, particle P moves along the x-axis such that for time t greater than 0, its position is given by x of p of t is equal to 6 minus 4e to the negative t. Particle Q moves along the y-axis such that for time t greater than 0, its velocity is given by v sub q of t is equal to 1 over t squared. And we know at time t equal 1, the position of particle Q is y sub q of 1 is equal to t. Now, just listening to some of the language, it's very easy for students to get frustrated by some of the notation. The subscripts of P and Q can be confusing, but really they're not designed to confuse. They're designed to really help the problem read a little bit easier and distinguish between which of the two particles. And of course, having the X used for the position of particle P and the Y being used for the position of particle Q really helps us discern which one is moving along which axis. Now, part A read, find v sub p of t, the velocity of particle P at time t. Now, obviously, this is not a calculator active question, so any kind of derivative and or integral that we would have to take would have to be done by hand. And part A is certainly going to require the computation of a derivative. And so the exemplary response would be for the student to recognize that we're finding v sub p of t, which is x sub p prime of t, which of course would give us the value 4e to the negative t. So the derivative that we're taking there is just a real simple chain rule, I suppose. The derivative of your 6 would be 0. And then for the derivative of the negative 4e to the negative t, really the only complicated matter there is applying the chain rule and getting another negative 1 factor that would cancel the initial negative out. And so obviously that part is not going to be worth a whole lot, 1 point on this particular exam, but there's just a very little bit of variation in what the student could write down to receive that point. It's probably going to be a little bit more lenient than you might imagine. So first of all, a response that equates x sub p with v sub p is going to be bad news. And you know, the reason why this is in the scoring notes is because in the pre-reading there were several of these kinds of responses that were encountered. And so we just have to make sure that the student doesn't somehow confuse position with velocity and thinking that they're the same thing. That notation, if the student chooses to write it, is going to be very important. In other words, v is the derivative of x, to put it very simply. Now, an unlabeled response will earn the point. And so if all that you see on the student's paper is 4e to the negative t, or negative 4e to the negative t, all times negative 1, that would be enough to earn the first point. We're going to look at the student's response and say they obviously knew that the derivative had to be taken and they took it correctly, so they would have earned the point. Obviously, that's a little bit different with the philosophy with calculator active questions, where a student would have to write down on their paper what kind of function that they were entering into their calculator, whether it be an integral or in this case, a derivative. For part B, find a sub q of t, the acceleration of particle q at time t, and find all times t for t greater than 0 when the speed of particle q is decreasing. And we have to justify our answer. Well, remember, particle q is the particle that's moving along the y-axis. We were given its velocity equation of 1 over t squared here. And so we are going to have to take the derivative of that 1 over t squared to get into the mode of acceleration. And so that initial part is just going to yield the -2 over t to the third power, and that in and of itself is going to earn the student the first point. Much like we took a derivative in problem A, we're going to take another derivative in problem B. Now keep in mind, this particular question does want two different things, and the second of which, finding the times when the speed is going to, I believe, decrease, is going to be very important. And I sort of have that covered up, so I want to make sure we're going to find the time when the speed of particle Q is indeed decreasing. So for that portion, what we'd have to do is know that our A sub Q that we found is clearly going to be negative whenever we plug in a t value that's greater than 0, as dispelled out here by the -2 over t to the third power. Now, the velocity of particle Q is also going to play a very prominent role in determining what's happening. And so we know that the velocity is 1 over t squared, and it really doesn't matter for any positive or negative time t, other than 0, of course, that we're going to end up with a positive result for that velocity. And so we have to somehow consider the signs of both acceleration and velocity. And there's a couple of different ways that students can do that to earn the first point that we can discuss here in the scoring notes. Once the student has determined that those two signs do have opposite relationships, then the student could go on to say that the speed of particle Q is going to decrease. And so that would, again, be the exemplary response that we would love all of our students to be able to state. But there are some variations, and we're going to take a look at those here in the scoring notes. So first of all, that first point. Earning that first point is not necessary for a response to still be eligible for the second or third points. However, the response must present some kind of an expression for the acceleration of particle Q at t to be eligible for that third point. In other words, students might take an incorrect derivative, but we don't want them to be out of all 3 points. We still want to read with them a little bit and see if they're still grasping the concept of when speed would be decreasing. And so we're going to do just that. And then a response would earn the second point with either of the following statements. V sub q of t and a sub q of t have opposite signs, or v sub q of t and a sub q of t have the same sign. Now that statement, however, must be consistent with v sub q of t and the presented expression for the a sub q. So what this is saying is if a student took the derivative incorrectly, and let's say for whatever reason they don't have a negative with their 2 in the numerator, we would go ahead and let them sacrifice that first point, but by starting to compare the signs, the students still back into our problem and thus can earn that second point, and hopefully, you know, the potential for the third point would still be there as well. Now, a response must earn that second point in order to be eligible for the third point. So they have to do some kind of a sign analysis, comparison, consideration. Now, that answer must be consistent with the presented justification. So in other words, if a student justified the speed being increasing, we're going to be okay with that as long as the student made the statement that the signs of A and V were, in this case, the same or both positive, I would assume. So the responses for which A sub q of t is greater than 0 for time greater than 0 must conclude that there's no time at which the speed of the particle is decreasing. So in other words, if they make the mistake with the acceleration, that mistake has to be considering the fact that v is always positive, right? We're not going to let them make 2 mistakes, in other words. And so they have to have the conclusion of speed increasing in order to receive the second and third point with that incorrect positive acceleration expression. All right. A response that indicates that v sub q of t is less than 0 will not earn that third point, even if the answer and the justification are consistent with the reported sign of a sub q of t. Okay, now the question then kind of is brought up. Can the student earn a 0-1-0 on this? Well, it's probably not likely that that's going to happen, but if a student makes a strong enough statement and they're considering their signs and for whatever reason has the V being negative in this case, we're going to go ahead and give them the potential to earn that second point only, but they cannot earn a third point if they've stated that the velocity is going to be negative. All right, part C of the question asks to find y sub q of t, which is the position of the particle q at time t. And so the exemplary response would show that the student is considering the initial condition, the position of the particle along the y-axis at time 1, and then accumulating some more displacement by integrating the expression 1 over s squared, which is indeed the velocity of particle q along the interval 1 to t. The student would have to resolve that integral by hand, of course. The integration of 1 over s squared would be negative 1 over s, and then evaluating that from 1 to t and simplifying would ultimately lead them to potentially 3 minus 1 over t. Now notice the student is going to earn a point for an integral. We're going to talk about what kind of details the integral must require to earn that point. And then in typical fashion, the initial condition, just the implementation of it into the answer is going to be worth a point. And then all of that is going to get sort of rewarded if the student resolves everything correctly with that answer point. And that actually does include taking the antiderivative correctly. Notice how this problem doesn't really award the student a simple antiderivative point, likely because that antiderivative is fairly simple to find. So let's take a look at the variations here for part C in the scoring notes. A response that presents the antiderivative of 1 over t squared with respect to t from 1 to t. In other words, we're using the same variable as the limit in the integrand function. In other words, we didn't use s, we used t. We're going to say that that does not earn the first point unless it is followed up by an attempt at integration. We don't like the fact that the student has really messed up the variables and is sort of kind of communicating something here that's not correct. But as you can see, if you do integrate, whether it was 1 over s squared or 1 over t squared, and then eventually plug in the boundaries 1 and t, you're going to have your expression in terms of t eventually. And so we're going to be okay as long as the student just didn't stop and not even consider an integral. Okay. Now notice it says unless followed by an attempt at integration. That doesn't mean that an attempt has to be accurate. So as long as they've made some kind of an integration answer as a presentation on their paper, they can still reap the benefits of that first point, albeit with an improper variable. All right, and taking a look at the second note here, a response that represents either the indefinite integral of 1 over t squared with respect to t, or negative 1 over t with no integral is going to earn that first point. All right. Again, it's not communicating very well, but we're going to go ahead and say that those two things are going to be enough to earn that first point. Because it is using the idea of the fact that we must integrate. Now, you might think, well, gosh, we're being pretty lenient here. I mean, if they don't put the boundaries, it's okay to leave it as integration of 1 over t squared. Well, yeah, it is, because we don't want those boundaries and that variable to be matching in this particular instance. We don't think that that's a very good entry point into the question. And so we'll allow that first point to be earned with an indefinite integral there. And of course, the negative 1 over t is a little bit better answer because that does show that the student made the attempt. Now, if the response continues and say it presents the fact that 2 is equal to negative 1 plus c value, then we're going to go ahead and award that second point because the student clearly used that initial condition of 2 correctly. Other scoring notes here. A response that presents only y sub q of t is equal to -1 over t plus 3. That is going to earn all 3 points. I mean, let's face it, that's our answer, right? And even if the right side is the only thing that's showing up on the student's paper, nothing written except -1 over t plus 3, that will earn points 1, 2, and 3. It seems like that's a little, I, I guess, minimalistic on the student's part, but the fact remains is that the fundamental theorem here is not real difficult for a bright student to see. The integral is very easy to take, and then possibly employing that constant and using the initial condition is something that a bright student could pull off in their head. So we're going to go ahead and give the student the benefit of the doubt on this particular problem and award all 3 points for a -1 over t plus 3. Now, a response that shows the y sub q of t being -1 over t plus c, as long as c is not equal to 3, so any other constant that has no additional work would only earn the integral point. We don't see them using the initial condition, right? Or they may have tried to, but they didn't do a very good job of communicating which one they used to get whatever value of C they found. And of course, their answer is incorrect. All right, taking a look at the last part, part D. As t approaches infinity, which particle will eventually be farther from the origin? Give a reason for your answer. And so we have to take a look at both of the particles and their behavior. And so for particle P, we're going to take the limit of its position expression, 6 minus 4 e to the negative t as t approaches infinity. And in that particular limit, we can see that the e to the negative t is going to essentially become 0 as t gets larger and larger, producing a result of 6. Now for particle Q, it's very important that we use the position expression that we got from part C, allow t to approach infinity there, and we can see that 3 would be the result. Now, in order to earn the first point, notice the student only needs one of those limits to be correct. We feel like they've demonstrated the fact that they know how to find a limit at infinity. Even though we wanted 2, we're only going to reward a 1 point anyway. And so one of those correct is going to end up giving us a point to award the student. Now, obviously, they're probably not going to have an ability to get the answer point correct. Now, for the answer, obviously, if 6 is larger than 3, particle P will eventually be farther from the origin because it has a longer, twice as much distance. And notice that these distances are measured along the x or the y axis, and so we can just take them for what they're worth and use them accordingly, 6 being bigger than 3. Okay, now some scoring notes here. A response with an incorrect y sub q of t from part C. We're going to say that it's eligible for both points in part D, provided that the velocity sub q of t is a non-constant function. Okay, and so we want something, we want a variable in there. In other words, we want there to be a t that we somehow have to allow to approach infinity and and see how it behaves accordingly. Now that second point is going to be earned for a consistent answer with a reason and the limits correct for particle P and the presented v sub q of t that we may have found. And so we have to have that consistency, right? So if we've messed up that previous v sub q and y sub q that resulted, then we can still get this second point as long as everything is consistent. We have our a p larger than our q in that particular instance. Responses that present statements like 6 minus 4 e to the negative t approaches 6, or q goes to 3, those will earn the first point. They don't present the limit quite the most formal way, but it does at least show that the student knew how to take the limit value. And we're going to also allow those responses to be eligible for the second point as long as they made the correct comparison there. All right. And then we have a response that treats infinity as an input for x sub p or y sub q. So in other words, a student directly replaces the t with an infinity in either or both expressions. That is not a great situation, and we're not going to allow those to be eligible for the second point at all. We're going to go ahead and at least acknowledge the fact that the limit was taken, it wasn't resolved or simplified correctly, but we're going to say that that's not allowing us to make a comparison with P or Q in the correct way. So we can allow the first point to be earned there, but we're not going to allow the second point to be earned. As far as this problem is from a historical perspective on that particular year's exam from a statistics standpoint, we have an average of 3.04, which is fairly low. Typically, these particle motion problems, they kind of vary a little bit. Oftentimes, they're found earlier in the exam with calculator active, which allows students to kind of squeeze in a few more points if they know how to manipulate some things with their calculator. But nonetheless, just slightly above 3 was the average for the 2022 AB6. Hopefully this takes care of any questions that you might have had about the scoring of this particular problem. And notice that we do have a couple of other videos that outline the scoring of ABPC 1 on that exam and BC number 2. So hopefully this has been helpful. And as always, we'll see you next time.